Hi, my name is Vignesh Balaji, and I'm a research scientist at the Architecture Research Group at NVIDIA. And today I'm going to be talking about our work on improving the locality of irregular updates with hardware-assisted propagation blocking. This was work that I did in collaboration with my PhD advisor, Brandon Lucia, at Carnegie Mellon University. The main problem that we address in our work is that many important applications perform irregular updates, which leads to an inefficient execution. The primary source of inefficiency in these irregular update workloads is poor cache locality. We measured the last level cache miss rate for a range of workloads spanning 4 different categories, and we found that across the board, these irregular update workloads have a consistently high last level cache miss rate, which essentially means that these workloads are dominated by DRAM accesses. Fortunately, there exists a software-based cache locality optimization called propagation blocking, which improves the locality of irregular updates. And we're going to explain how propagation blocking works in the context of a standard graph analytics kernel. The key problem with graph analytics kernel and irregular update workloads in general is that they have a large irregular update range. For graph analytics workloads, the irregular update range is often the number of vertices in the graph, which is much larger than what can fit in a typical last level cache. So the way propagation blocking improves such a workload is by dividing the execution into 2 phases, binning followed by accumulate. In the first phase of propagation blocking, which is binning, the core essentially does not perform any irregular updates. It only generates update tuples. An update tuple is a collection of an index location and the value that needs to be applied at a particular index location. For each of these update tuples, the core writes them into one of many data structures called bins. The key defining property of a bin is that they store update tuples for disjoint ranges of indices. So if we have an update tuple with the index in the range 0 to v by 4, then that particular update tuple will be written to bin 0. In this fashion, during the binning phase, the core essentially generates update tuples and writes it into one of many bins. And once all the update tuples are written into the corresponding bins, the binning phase is complete and we are ready to move on to the accumulate phase. In the accumulate phase, we essentially process all the update tuples of a particular bin before moving on to the update tuples of the next bin. And now, because each bin stores update tuples for a limited range of indices, when we apply the irregular updates in the accumulate phase, the irregular update range went from V to V divided by bins. So by using the bin data structure, propagation blocking is able to reorganize the irregular updates, thereby improving locality. And by using the bin data structure, propagation blocking is able to improve the locality of many irregular update workloads. What we can see on the slide is that propagation blocking is a pretty versatile software optimization because it is able to provide performance improvements for these broad range of workloads. Unfortunately, despite these impressive results, we are going to show later that propagation blocking executions are still suboptimal because they suffer from certain limitations, which we'll try to address using architecture support. The primary limitation of propagation blocking is that it is unable to use the optimal number of bins. To appreciate that point, let's focus on the accumulate phase. We saw that the accumulate phase irregular update range is equal to V divided by bins. So the optimal performance for accumulate phase will be achieved when we have a large number of bins such that all the irregular updates fit in the L1 cache. And that's what we see in our performance characterization on the bottom left. Unfortunately, if we were to plot the binning phase performance as a number of bins, we see that it has the exact inverse relationship with the number of bins, with the worst binning performance when there are a large number of bins. So essentially for this reason, we are unable to use the optimal number of bins in propagation blocking, which is a large number of bins. So the key insight of our work is to improve propagation blocking performance. We essentially target improving binning performance when there are a large number of bins. Using architecture support, we want to eliminate the binning tax of propagation blocking. So to understand why binning performance deteriorates when there are a large number of bins, we need to introduce an implementation detail, which is that during the binning phase, the core does not directly write update tuples into bins. Instead, the core first writes the update tuples into one of many coalescing buffers or C buffers. These are cache line size containers, and there's one C buffer per bin. These C buffers essentially collect update tuples for a particular bin and then do a bulk transfer. And now we can see why binning performance deteriorates when there are a large number of bins. When there are a small number of bins, there's a correspondingly small number of C buffers. But as the number of bins in memory increases, so does the number of C buffers. to the point that we can no longer fit all the C buffers in the L1 cache, and hence we have a high binning latency. So the key insight of our work, which we call Cobra, is that we want to decouple binning performance from the number of bins in memory. And the way we do that is by, instead of having one set of C buffers, we have a hierarchy of C buffers with each cache level having its own set of C buffers. And in a Cobra execution, during the binning phase, the core basically only interacts with the L1C buffers. So at some point when an L1C buffer fills up, unlike in a vanilla propagation blocking execution where we directly flush the contents to an in-memory bin, in a Cobra execution, when an L1C buffer fills up, we evict the contents into one of many L2C buffers. And an important design detail is that these C buffer eviction operations are not on the critical path. Using very limited buffering between cache levels, we can ensure that these eviction operations are off the critical path. Similarly, at some later point, when an L2C buffer fills up, we evict the contents into one of many L3C buffers. And finally, when an L3C buffer fills up, at this point, we actually flush the contents to an in-memory bin. So in this fashion, in a Cobra execution, the core generates update tuples and writes them into the L1C buffers. And then in the background, they're evicted into the L2C buffers, then to the L3C buffers before eventually being written into in-memory bins. So in a Cobra execution, we are able to support a large number of in-memory bins. That's only bounded by how many L3C buffers we can have. But as far as the core is concerned, it only interacts with a small number of L1C buffers. So in a Cobra execution during the binning phase, we have a large number of bins in memory. But as far as the core is concerned, the effective binning latency is as if there are a small number of bins. So using the decoupled architecture of Cobra, we are able to provide propagation blocking with the optimal number of bins. And for this reason, Cobra provides significant performance improvement over propagation blocking. Propagation blocking was already a very versatile optimization. By targeting hardware for propagation blocking, we're able to provide performance improvements for a broad range of kernels. In summary, Cobra is able to provide an average speedup of 1.75x over propagation blocking and 3.2x over the baseline cache and optimized version of these workloads. So in summary, in this work, we studied propagation blocking, which is a pretty versatile software-based cache locality optimization. We showed that propagation blocking in software suffers from a limitation of not being able to use the optimal number of bins. And then we proposed Cobra, which is an architecture designed to optimize propagation blocking. Specifically, Cobra uses a hierarchy of hardware managed C buffers to improve binning performance when there are a large number of bins. There's a lot more details that can be found in the paper. So please check out our paper. And now I'd be happy to answer your questions.